This is the end of week 2. We're almost halfway through the course. And what I want to do today is round out what we've been doing with a single quantum spin so that we can change topic next week. There, I want to get to what happens when we have two quantum spins so that we can start to talk about ideas like quantum entanglement. I want to extend quantum mechanics out into position and momentum. And then I want to look at uncertainty principles before we finish my half of the course. Just to motivate today's lecture, what I want to do is bring up a slide from lecture 1. And this slide actually came at the end of a long series of measurements with a sort of our Qtron, or basically a Stern-Gerlach experiment in a box, of what the outcome of trying to measure the projection of a spin along some direction is, right? And so you'll remember there we started out looking at what happens if you have your magnetic field along Z and you put all sorts of different spins in, and then we looked along X, and then we looked at repeated measurements of switching X and Z. And then right at the end, we basically went and looked at the case where we put a spin pointing along some arbitrary direction in and the measuring apparatus pointing in some arbitrary direction. And I said, we'll come back to this later, but the results depend on the angle between the spin that's come in and the axis that you're trying to measure, okay? And we got these sort of trigonometric relations in here. What I wanted to do today is actually take that as the end point for dealing with our quantum spin and pull all the pieces we've had together so far to get to this point where we can actually work out what the probability of getting a spin along the axis and anti-aligned to that axis is for some arbitrary axis direction, and also work out what the expectation value for that is, okay? So let me build up to this problem from where we were yesterday, where we had our Pauli matrices sigma x, sigma y, sigma z. Okay, you remember we had a set of 2 by 2 matrices yesterday, and in particular sigma z for the up-down basis has the eigenvalues 1 and -1 on the diagonal. Okay, those 3 matrices basically deal with measurements of the angular momentum component along the axes z, y, and x. And what we can do here is sort of start to bring gradually back together our 2D complex vector space, Hilbert space world, where we're dealing with state vectors and things like that, and our real world where we have, a X direction, a Z direction, and a Y direction, okay? So what we're going to do here, just to start, is we're going to make a general spin operator. We're going to call it sigma, and it's going to be a vector operator. Okay, so one thing we know so far is that all our operators are matrices. So you might initially be asking yourself, well, how do we combine a matrix into a vector? It's pretty easy. You make a thing that we basically call a matrix vector. Okay, so what this thing is essentially the sum of the sigma x matrix times a unit vector along x plus the sigma y matrix times a unit vector along j, the y direction, and a sigma z matrix times the unit vector along k. And so one way to write this is essentially as a vector. So it's something that has a direction. And the components, rather than being single numbers, those components are just matrices. Okay, that's why we call it a matrix vector. It's a vector made up with matrix components to it. Okay, and really all we're doing here is building ourselves a single matrix where the form that the matrix takes depends on the direction that you're looking in. Okay, this will become pretty obvious to you in a second once I write another form for this particular Pauli vector operator here. Okay, so I want you to just think about this vector here for a moment. I'll bring up some writing paper. If we think about our vector here, sigma x I, sigma y j, sigma z k. And imagine for a second what we do is we take that vector and we make a dot product with the k vector, right? What does this do? What we would get here would be, you know that the k vector is 0, 0, 1, right? So 0 for I, 0 for j, 1 for k. So this would be sigma x times 0 plus sigma y times 0 plus sigma z times 1, which would just give us sigma z, okay? And you can imagine I could do the same thing. I could take the dot product of my sigma, my Pauli vector, and j hat, and I would get sigma y. And I could take my dot product of my Pauli vector and I hat, and I would get sigma x, right? I can pick out any particular direction by taking a dot product. So the interesting question that we're trying to ask here is, if we think back to our spin analyzer device, there's no reason why the direction for that analyzer, the magnetic field that we use in the Stern-Gerlach experiment, for example, needs to point necessarily along Z or Y or X. It could point along any general direction, okay? And the way we can get it to point along any general direction that we like is to basically take the dot product with some arbitrary direction n hat, and that's basically just a vector that points any way we want. So if we basically wanted to go that way, we would just define an n hat that points that way, that would have some components nz, nx, and ny. Okay, all right. So now we have sort of an equivalent of a Pauli matrix for any particular direction that we might be interested in. And let's have a quick look at what this looks like, okay? So we have a sigma n, and that sigma n is equal to our Pauli vector and the dot product of our direction of interest n hat, okay? This thing would be sigma x nx plus sigma y ny plus sigma z nz. And so we could take this one step further and now just write this as a set of matrices, right? So what we would have is nx here, and we would put our Pauli matrix 0, 1, 1, 0, plus ny 0 minus I, 0, plus nz 1 minus 1, 0, 0 in here, okay? Now, one thing you know about matrices is that you can just add them up, right? So we can basically multiply the n into the matrix, add those matrices together, and get a matrix that looks like this. nz, nx plus I ny, nx minus I ny, and minus nz down the bottom here. Okay? And so now we have a sort of a special Pauli matrix that, depending on which direction it points in, has a slightly different value, right? And if you imagine that we're interested in it pointing along Z, then nz would be 1, nx would be 0, and ny would be 0. And if you put those into that equation there, the two terms on the diagonals here will go to 0. The two terms on the off diagonal will go to 0. The two terms on the diagonal will go to +1 and -1. And so we would end up back with our normal Pauli matrix that we have in sigma z just up the top here, okay? All right, so we've built this thing. What I now want to do is test it with a special case. If you have a look at the form of this matrix here, what you'll notice is that it could get very complicated very quickly because we've got imaginary terms in the two off diagonals and so forth, okay? So what I'm going to do today is deal with this with a special case, which is n hat in the xz plane, just to keep things nice and simple. And you can do for yourself as an exercise just what would happen if I did it in y, or what would happen if I did it in zy instead, or so forth, just to give yourself some practice, okay? So if we now want to consider that plane, let's draw something up here. What we would have is, this is our x direction, this is our z direction up here. What we would have is a unit vector n hat. It would have some component in the x direction nx, some component in the z direction nz. Our ny would be 0 here because we've collapsed it into the plane. And what we could do is define some angle theta here to the z-axis. And what we would know here is that nx is equal to sine theta, ny is equal to 0, and nz would be equal to cos theta. And you'll notice that I've got no prefactors in those because n hat is a unit vector, so it's got a length of 1, okay? All right, so what we can do is take our Pauli matrix up there, which is a general thing for x, y, and z, and now we can just collapse it down into the xz plane to keep things nice and simple, okay? So now what we would have is a simpler expression for sigma n, which would simply be our nz on the top left element, so cos theta up here, minus cos theta in the bottom right. And then the off diagonal elements, there's a 0 for ny, so we would just have our nx. So these would be sine theta and sine theta, respectively. Sine theta, sine theta. Okay? Bit of a simpler problem to deal with, just so that we can keep it inside the space of a normal lecture. So what I want to do in the two separate halves of this lecture, the first half, what I want to do is actually get out what the eigenvalues and eigenvectors are for this matrix, okay? The last few lectures, you'll have seen me say, oh, the whole reason for a sigma is to get the eigenvalues and the eigenvectors, but you'll also be going, well, hang on a second, he used the eigenvalues and eigenvectors to get the matrix in the first place. Isn't this kind of just a bit trivial and circular? And it sort of is when you do it for that first case, but in a lot of cases, what you will do is you will adapt problems when you get to bigger problems where your first entry point will be the matrix operator, and your job is to then go and work out what the eigenvalues and the eigenvectors are, so that you can work out, what the basis states are and what the measurable outcomes are and stuff like that. And you can imagine having that the case here, right? We've arrived at some matrix operator, and now we want to know what the eigenvalues and eigenvectors are, so that we can actually start making some understanding of what's going on in here. Okay, so we know we've got a quantum spin system here, and it's a 2 by 2 matrix. So we would expect to have 2 eigenvectors and 2 eigenvalues pop out of this thing, okay? And we would expect that we can probably call them lambda 1 and lambda 2. And we would expect from the problems that we've been dealing so far, because of where we've taken it from to build this, we would probably expect that our eigenvalues are going to be +1 and -1, okay? We're not going to assume that a priori, but what we'll show is that that's the case, okay? Now, what we could do here is basically write a starting guess position for what the eigenvector is going to look like, right? This is a really common approach in physics. Often you kind of can't just start from nothing. So what you do is you start from a very good educated guess, and either that educated guess is right, in which case you kind of got lucky, or that educated guess is bad, and what you learn by that educated guess being bad enables you to make an even better guess, and hopefully the second time you get it. If you don't get it the second time, hopefully you're closer. Then you just keep going until you get the right thing, right? And this is probably one of the cruelties of undergraduate, is that you don't get to see all the mistakes that get made on the way. So what we're going to do is guess a form for our eigen vector here, and we're not going to call it 1 or 2. We're just going to call it lambda, because what we should find out is that there's 2 possible ways to write this thing, okay? And our guess in here, and it's probably as good as any, and it's a little bit of an educated guess in this case because I know the answer, but you could decide to make this on the basis of what your matrix looks like, for example. We're going to call this cos alpha and sine alpha. We don't know what alpha is yet, okay? And what we're going to specify in here is that it obeys an eigenequation that looks like this. Sigma n acting on our eigenvector lambda will be equal to lambda times lambda, okay? Standard eigenvector equation, and often very commonplace to start to approaching this, right? So what we're going to do now is we're going to write this in matrix form. So let's do that. We've got, let's just pull this down for a second, cos theta sine theta sine theta minus cos theta times cos alpha sine alpha equals lambda cos alpha sine alpha, like so. Okay, so this is just our eigenvalue equation written in proper form. And up the top on the left-hand side here, what we've got is a matrix times a vector, and we can do that product. Okay, so let's work through and do that real quick. What we're going to get is a much bigger matrix that looks like cos theta cos alpha plus sine theta sine alpha. And then the other term is going to be sine theta cos alpha minus cos theta sine alpha. Okay, and of course this is a matrix, 2 by 2 matrix by a column vector. So what we're going to get is a column vector. Okay, so there's two elements in this: one on the top, one on the bottom, one column in this thing. Okay, so that will be that. Okay, what you'll remember from your linear algebra classes is that you can basically treat this as a simultaneous equation. Talked about this in the last lecture, right? So we can split this off into two simultaneous equations: cos theta cos alpha plus sine theta sine alpha is equal to lambda cos alpha. Call that number one. And sine theta cos alpha minus cos theta sine alpha is equal to lambda sine alpha, and that's number two. Okay, at this point we're going to be feeling kind of comfortable. We have two equations which should give us two different answers, and of course that's what we're looking for, right? We're looking for two eigenvectors, we're looking for two eigenvalues, and we have two equations to get them out. All right, okay. So at this point, we need some mathematical relations. In the last lecture, I talked about the book of maths. This is when I'd be reaching for my book of maths or the equation sheet on the front of the exam if it was an exam question. And so what we're going to use here is two relations. One is that cos alpha cos theta cos alpha plus sine theta sine alpha is equal to cos theta minus alpha. And the other one is that sine theta cos alpha minus cos theta sine alpha is equal to sine theta minus alpha. Okay, should have seen those in first year, may even have seen them in high school because I remember being taught these in high school as well. Okay, so what I want to do here is now take my equations 1 and 2 and reduce them down. Okay, so let's take equation 1, and what we'll use is this first relation to simplify it. So what we would have is cos theta minus alpha is equal to lambda cos alpha. And then my second one here, what I'm going to do is call this sine theta minus alpha equals lambda sine alpha. Okay, so I've still got two equations to work with here. What I can do here is rewrite both of these two equations in terms of lambda and make them equal to each other. So let's do that. I can take the first one and I can write it as lambda is equal to cos theta minus alpha on cos alpha. I can take my second one and I can write it as lambda equals sine theta minus alpha on sine alpha as well. And then I can take the two lambdas and make them equal to each other and give myself an entry point for solving these two equations. So what I would have is cos theta minus alpha on cos alpha is equal to sine theta minus alpha on sine alpha. Okay. And again, this is one of these things you kind of learn when you do enough problems in physics and mathematics too, is that, you know, you sort of start to pick up what are the smart approaches to attack various types of problems, like this one where you've got two simultaneous equations. You remember in the last lecture, we kind of did a substitution from one side to the other. That's one approach. This approach here is basically to isolate the term that's going to be common between the two and make the two things equal, right? These are all just sort of catalogs of approaches for solving things like simultaneous equations. Okay, so at this point here, we'd cross multiply. Okay, so let's do that. Cos theta minus alpha sine alpha is equal to sine theta minus alpha cos alpha. And then we can take one of the terms from one side over to the other so that we can make this thing equal to 0. Okay, so cos theta minus alpha sine alpha minus sine theta minus alpha cos alpha would be equal to 0. Okay. Now, if you remember, we had a relationship up here that looked like this, right? Sine of theta cos alpha minus cos alpha, cos theta sine alpha is equal to something. And you'll notice that this equation here kind of looks like it if I reverse the sine and cos in the front and I reverse the sine and cos in the back. And you know that two terms being multiplied that are sine and cos functions, we can just swap here, okay? So this thing we could write as sine alpha minus theta minus alpha in here. If you don't believe me, you can have a look at my notes. I do the intermediate step just to be really pedantic about it. So it will look like this. And then, of course, we can expand that bracket out. So what we would get here is sine 2 alpha minus theta is equal to 0. Okay? And this is now at the point where we can basically solve our simultaneous equations. We know what we have to do to make a sine function equal to 0. There's two possibilities here, right? Possibility 1 is that 2 alpha minus theta is equal to 0. And that would be a mod 2 pi thing, right? Or a mod pi thing. And the other possibility that we have here is 2 alpha minus theta is equal to pi, right? If you think about a sine function, it's the one that starts at the origin and does this. And so the places where it's equal to 0 is 0, pi, 2 pi, 3 pi, so forth. 0, 2 pi, 4 pi are one group. Pi, 3 pi, 5 pi are the other group. Okay? So now we're sort of heading towards two possible classes of solution, right? And we can drop out the higher pi numbers here to keep things nice and simple. This one here would basically reduce quite simply to, we can take the theta on the other side and divide by 2. So this will be alpha equals theta on 2. And then this one down here, we have to keep the pi. So what we would do is take the theta over to the other side and then divide by 2. So here we have alpha is equal to theta on 2 plus pi on 2. Okay, and you can imagine that the modulo solutions hang out the back of that, but they're all equivalent, and so you don't really need them. Okay, so these are now our two solutions, and we can deal with them one by one here. Okay, so what we're going to do here is call the first one lambda 1, right? Let's call this one 3 and this one 4. So what we're going to do is deal with 3 first. So we're going to call this lambda 1, and what it's going to be is you remember that we defined our lambda right up the top. Where is it? Just here. We defined our lambda as cos theta minus alpha on cos alpha. Okay, so our first one will be cos. Let me clean this up with an eraser for a second. Cos theta minus alpha on cos alpha. And we can now pop in here and make this for the case where alpha equals theta on 2. Okay, so what we would have is cos theta minus theta on 2 on cos theta on 2. And of course, this thing at the top is basically just cos theta on 2 on cos theta on 2. And this is just plus 1. Okay? Now, one thing you'll notice for yourself, let me just, I sort of glossed over it. I want to come back to it. What we did was we basically said we have two eigenvalues, and what we'll do is we'll call them just one lambda at the moment. And then we'll hopefully end up with two solutions, which we just did, this 3 and 4, which are two different cases of alpha, okay? What we're now doing is feeding that back into that equation that we had for our eigenvalue here. And what you'll notice is that we can write it as cos theta minus alpha on cos alpha, but we can equivalently write it as sine theta minus alpha on sine alpha. You can do the other version for yourself and you'll find that you get the same answers, right? So in here, you could stick the sine version in and you should get the same answer for both of the times we do this, okay? All right, so then the other thing that we would do here is find out what the corresponding eigenvector is. And of course, earlier we wrote this as our guess cos alpha on, sorry, not cos alpha, on cos alpha and sine alpha as your two elements. Like so, this would now be cos theta on 2 and sine theta on 2 just here. Okay, so that's our first eigenvector and its corresponding eigenvalue. We can do this for 4 as well, and 4 ends up being slightly trickier, but I'll work through it. So this one now we'll call it lambda 2. Getting a bit late in the evening today, so hopefully I don't make too many mistakes from here. And we can do this again by the same logic. So this will be cos theta minus alpha on cos alpha. And you could do it by the sine as well, just to prove to yourself that I'm not telling you a furphy here. It works either way. So this would now be cos theta minus theta on 2 minus pi on 2. Okay, because it's what we're using is this solution number 4 just here, where we have the plus, but we're subtracting the alpha in just here. On cos theta on 2 plus pi on 2, like so. And then this thing here, we can reduce these guys out. So this will now be cos theta on 2 minus pi on 2 divided by cos theta on 2 plus pi on 2, like so. Okay. And then you'll remember we had our trig relations way back up here somewhere. So what we can do is use this one. We can now take our sum and our difference and convert them back into terms in cos and sine. So just to be really clear on this one, if this is minus plus over here, this will be plus minus, okay? So what we would have down here would be, let me just see if I can get it right in the light, cos theta on 2 cos pi on 2 plus sine theta on 2 sine pi on 2. The minus sign gives you the plus sign on cos, oops, it's interesting, spontaneously changed color. Cos theta on 2 cos pi on 2 minus sine theta on 2 sine pi on 2, just there, okay? Of course, what we know here is that cos pi on 2 is equal to 0 and sine pi on 2 is equal to 1, right? We just know these for cos functions. So this term here is how do I do this? What's the best way to do it? Let me use the red pen to point it out. This one here is 0. This one here is 0. This one here is 1, and this one here is 1. So what we will end up with here is sine theta on 2 on minus sine theta on 2. And of course, that's equal to minus 1. And then the last step in here would be to get lambda 2, the eigenvector. And so it will be cos theta on 2 plus pi on 2 sine theta on 2 plus pi on 2. And of course, we can do exactly the same expansion that we did in the previous part for the eigenvalue. So this would now be cos theta on 2 cos pi on 2 minus sine theta on 2 sine pi on 2 for the top term. And then for the bottom one, we've got to come back and use this second term just here. And we know that if we got a minus sign on this side, we get a minus sign over here. And if we've got a plus sign in here, we get a plus sign in here. Okay, so if we come back down to here, we get Let's just change color. Sine theta on 2 cos pi on 2 plus cos theta on 2 sine pi on 2. Let me just clean this up because it's pretty sloppy in here. Give me a black pen. Cos theta on 2, like so. And by the same argument that we just had, this is 0, this is 0, this is 1, and this is 1. So what we would be left with here is our sine theta on 2 with a minus at the top, sine theta on 2. So that's that term, and we would be left with this one here too, which would be cos theta on 2. Okay. I'll leave this as an exercise, and that's to show that lambda 1, lambda 2 inner product is equal to 0 here. Okay, just to check that these two eigen vectors that we get, this one here and this one here, are orthogonal to each other. But you can kind of see it quickly, right? You're going to get, when you do that product, you're going to get two terms that basically one's positive, one's negative. They cancel each other out and you get 0. Okay, so where we're at now is this position here. We have two eigenvectors that have a form that looks like cos theta on 2 and sine theta on 2 as the elements. And in the two cases, they're one way round and the other way round. And we have two eigenvalues here that are +1 and -1, which actually make us feel pretty good at this point because that's kind of what we would expect. Okay, so what this is telling us is that our educated guess to start this problem was probably pretty good. And aside from the fact that we know it was pretty good because we're doing a lecture, it was a good place to start. And we know it's a good place to start because we get values that don't make us feel really uncomfortable that something's gone wrong. Okay, so I'll stop here for the first half, take a quick break. And in the second half, what I want to do now is take these eigenvalues and eigenvectors and work on getting probabilities out and expectation values out for this problem so we can finish off this whole quantum spin stuff.